Hello, everyone, and welcome to partial fractions. So partial fraction is really just an algebraic tricks in order to integrate rational functions of the form P over Q, where Q is a quadratic equation. So it's not a new technique of integration. It's just how do you manipulate rational functions in order to compute indefinite integrals. And here, all our rational functions, their denominators, are going to be quadratic equations. You can extend partial fractions to rational functions in general, but this will not be the content of this section. So the goal is to compute indefinite integrals for rational functions of the form px over qx, where qx is a quadratic equation of the form ax squared plus bx plus c. So what I'll do, I'll just go over examples and just study these cases by looking at examples, concrete examples, one by one. The first thing that you always do, so I'm going to start with an example that is more like a remark because it's not something new. Like the first thing you always do if you have a rational function in your face is you try substitution, because some of those questions are just substitution questions where you don't need any new tricks. So for example, if you have to integrate x minus 2 over x squared minus 4x plus 7, let's try to use the denominator for a u substitution. So let's set up u equal to x squared minus 4x plus 7. So poof. So if you try this, what are you going to get? Well, you're going to get, for the derivative, if you compute the derivative of u, so du over dx, poof, you're going to get 2x minus 4. And then if you isolate dx, just by swapping the 2x minus 4 into dx, you're going to get that du over 2x minus 4 is dx. So here we go, poof. So we have a formula for the denominator. X squared minus 4x plus 7 is going to be replaced by u, and dx is going to blow up as du over 2x minus 4. So here we go. So we just play the game now. So this integral will become, with respect to u, poof, the following. So again here, just take your time, make sure that you substitute everything. So the denominator becomes u, the dx becomes du over 2x minus 4. And then, of course, this x minus 2, the numerator, you want to simplify it. And that's why if you factor the 2 out of the 2x minus 4, then you can see nicely, yes, it's always good. You can see nicely that the x minus 2 at the numerator and the one at the denominator, they cancel perfectly. So when you look at the rest of your integral now, you can see that this now becomes simply 1/2 the integral of 1 over u du. Now it's a basic integral with respect to u, so you get 1/2 ln of absolute value of u plus c, where u is x squared minus 4x plus 7. So again here, this is nothing new. This is just a regular substitution. In other words, if you choose u as the denominator, and if the derivative of the denominator is a multiple of the numerator, just use regular substitution and you're going to be done, okay, with that question. So remember, substitution is crucial. If you try to use the new tricks on something simpler, it might work, but you're going to work for it. Okay, so substitution first. Okay, remember this. Our next example is going to be the first example that is a bit more complex, where you cannot just use substitution to finish the question. So now we're looking at rational expression where the numerator is a polynomial of degree at most 1 and the denominator is a quadratic equation, so something of degree 2. And so for case 1, in case 1, the quadratic equation has only one root. So case 1 is for one root. In other words, the discriminant, the delta, the b squared minus 4ac is equal to 0. So in that case, once you find that one root, suppose that root is h, you're going to use a substitution u equal x minus h to finish that question. So let's do an example like this right away. So here we want to integrate x minus 1 over x squared minus 4x plus 4. And just as a remark here, if you try to use u equal to x squared minus 4x plus 4, so think about it. Well, the derivative would be 2x minus 4, and x minus 1 is not a multiple of 2x minus 4, so you cannot use that substitution to finish that question. But this quadratic equation, x squared minus 4x plus 4, can be factored as x minus 2 squared. So it's a nice square. It's a perfect square. So here, x minus 1, I'm keeping it like this for now, but the denominator is x minus 2 squared. So it has only one root, that root being 2. So right away, the correct substitution is going to be u equal that linear factor, that unique factor, x minus 2. In these questions, typically, you also need a formula for x. So if you bring the 2 on the left side, you're going to get u plus 2 is equal to x. So I have a formula for u, I have a formula for x. So if you compute the derivative of u with respect to x, you're just going to get 1. So if you just swap those two terms, you get that du is equal to dx. So we have also a formula for dx. So very crucial here, we have a formula for u, we have a formula for dx, and if needed, and in case we will need it, we also have a formula for x. So let's just substitute all that information in our problem. All right, it's substitution time. So here, the first thing I'm going to do at the denominator, I'm going to replace x minus 2 is going to become u, so squared, and then dx is going to simply be replaced by du, and at the numerator, x minus 1, so now I'm going to replace x by its formula with respect to u, which is u plus 2. So you're going to get u plus 2 minus 1. And now at this point, it's just to simplify, so it's purely algebraic. So here, u plus 2 minus 1 is just u plus 1. So you get the integral of u plus 1 over u squared du. Now if you just divide by u squared, you're going to get 1 over u plus 1 over u squared du. 1 over u is ln u in absolute value. And u squared, remember, it's u to the power minus 2, so it becomes u to the power minus 1 over minus 1, or minus 1 over u plus c. And now you just need to replace u by its original substitution. So ln of x minus 2 minus 1 over x minus 2 plus c. And that's it. That's all. So here for case 1, it's basically just remembering that if the quadratic equation is a square, is a pure, perfect square, so only one root, discriminant is 0, just use the linear factor, x minus h, as the u substitution, where h is that unique root. All right, that's it for case 1. Okay, just regular substitution, but just being guided to the linear factor. Next example. This example is the reason why this section is called partial fraction. So the case 2, the reason why I call this the case 2, because it's the case when the denominator has 2 roots. In other words, if you want to be a creep, the discriminant delta, so b squared minus 4ac, is strictly positive. So in that case, what's really amazing is that you can rewrite your question as the sum of 2 mini fractions. And these 2 mini fractions, they can be integrated very, very simply. And the best way just to learn this is just by going through an example and just to understand first that the integration part of this question is very straightforward. And the computations involved behind partial fractions are purely algebraic. Anyways, let's look at this first example. Let's integrate 2x plus 2 over x squared plus x minus 2. Again here, always think about substitution. If you try to use u as x squared plus x minus 2, the derivative would be 2x plus 1, which is not a multiple of 2x plus 2, so that won't work. So you cannot use u substitution to finish that question. But the denominator here, if you try to factor it, if you're looking for two numbers that multiplies to minus 2 and sums up to 1, well, you can do that. You can use x plus 2 times x plus 1. So this integral is the same thing. So since there's two roots here, you can write this. So you can factor the denominator. So the first step is just factorization. So we have x plus 2 times x plus 1. So we know we have a case 2, x minus 1. So we have a case 2 because we can factor it with two distinct linear factor. And now this integral, and this is the beautiful part of this question. So the trick is we don't know how exactly, but that doesn't matter for now. You can take this ugly piece of equation and break it. Okay, so I'm breaking it into two smaller fractions where you don't know what the coefficient is going to be at the numerator, but that's a computation that we're going to do afterwards. So you can write this as two mini fractions where the first fraction is a over x plus 2, and the second fraction is b over x minus 1. We don't know what a and b are. We just know they're numbers. But the point is, you don't give a shit. Oops, sorry about the language. You don't care what a and b are. You can actually do the integration part because you know the integral of 1 over x plus 2 is ln of absolute value of x plus 2. And you know the integral of 1 over b minus x minus 1 is ln of absolute value of x minus 1. So the integration part, we don't know what a and b are, but we don't care. They're just coefficients. So you can integrate. So actually, the integration part is done. And the only thing we need to figure out now is what are the values of a and b. And to do this, we just do this side computation. So we just take a moment where we're going to compute these values on the side and figure out these values on the side. So here, what do we want? So we need to find this a and b. So we want a and b such that if you combine these two fractions, a over x plus 2 plus b over x minus 1, you're going to recreate the original fraction, which is 2x plus 2 over x plus 2 times x minus 1. So on the left side, what you need to do is you need to combine these two fractions using common denominator. So you're going to cross multiply. So here a is going to multiply x minus 1 and b is going to multiply x plus 2 to get to the numerator on the right side, which is 2x plus 2. And here you don't care about denominators anymore. You just want to make sure that the top parts matches. So you want a and b such that a times x minus 1 plus b times x plus 2 is equal to 2x plus 2. And this needs to be true for every single x value. So the trick here is to choose some x values that will allow us to compute one of those two variables directly. Like for example, there's a nice x value here that will make this bracket equal to 0 and it's x equal 1. So here for x equal 1, so if you choose x equal 1, your equation will become the following one. So a times 1 minus 1 plus b times 1 plus 2. And then, of course, if you evaluate whatever you do on the left side, you do the exact same thing on the right side. So you replace x by 1. So you get 2 times 1 plus 2. And of course, even if we don't know a, we don't care. It's multiplied by 0. And you're left with 1 plus 2 times b, which is 3b, is equal to 4. And then just by dividing by 3, et voila. Okay, we have 4 over 3. So mystery solved here. Now we have a value for b. So the only thing we have to do now is find a value for a. And then I'm going to use the exact same trick here. I'm going to find the next value that will make this bubble equal to 0. Of course, you could do anything now that you know a, but might as well just keep the little trick alive. So for example, if I pick x equal minus 2, then you're going to get a times minus 2 minus 1 plus b, even if we know b here, minus 2 plus 2, which will give us a nice 0, 2 times minus 2 plus 2. So a will be multiplied by minus 3, b will be multiplied by 0, so bye-bye là. So you get minus 3a is equal to minus 4 plus 2, which is minus 2. If you divide by minus 3, you're going to get 2/3. Now that we have our two coefficients, we can finally write the final answer using those values that we freshly found. So the final answer, by replacing a by 2/3 and b by 4/3, is the following. Boom! Okay, so we have 2/3 times the ln of absolute value of x plus 2 plus 4/3 ln of absolute value of x minus 1 plus c. And that's it, that's all. So the trick again in a nutshell, if your denominator is a quadratic equation where you have two roots, you take your rational function, you break it into two pieces. The integration part will be very straightforward because the numerator of those two little mini fractions are going to be constants or coefficients. So you can do the integration part and just get your answer with those unknown coefficients a and b. And then on the side, okay, you just figure out what a and b are by just using basic algebraic tricks coming from common, oh my god, denominators. All right, but the case 2 is the reason why this section is called partial fractions, because case 1 or the one after case 3 are not partial fraction cases, but this is like one of the, it's the one where you don't really use substitution, you really use algebra to get it. Anyways, like, I'll shut up now. Okay, so anyways, for that video, that's it, that's all. The beautiful case 2. Bye-bye.